Welcome to Math 1314, section 4.3. In this section, we are looking at logarithmic functions. Now, logarithmic functions look like f of x equals log b of x. This b here is the base, and just like previously, this base b cannot be 0, cannot be 1, and cannot be negative. If the b is bigger than 1, that's a valid b, you can have b equals 10. And if the base is 10, you have f of x as log 10 of x. And this is given a name. It's called the common log. And on your calculator, it looks like a button with an LOG on it. If the base is e, then we have f of x is log e of x. But no one ever writes it with the e. It's always shortened to be ln of x. ln for natural log. This particular log function occurs often in natural processes. And on your calculator, it's a button that looks like a lowercase l and an n. Another b could be 2, and this would be log 2 of x. So all of these b's are b's that are bigger than 1. And if you look at the graph for that particular log function, what does it look like? Well, it crosses always at 1, 0. It grows as you go to the right, but it grows very, very slowly. And then when you look here at the origin, it runs off toward minus infinity the closer that you get to 0. So the domain for these functions starts at 0, does not include 0, and goes to the right forever. And the range, well, the range is everything. We do have a vertical asymptote here at x equals 0 because the graph never gets there. We could have b be a number between 0 and 1. I could have b equals a half. Then this would look like log 1/2 of x. Or b could be 2/5, and it looks like log 2/5 of x. It looks similar to the other graph, and that is it crosses at 1, 0. We do get a vertical asymptote here at x equals 0. Domain is exactly the same, does not include 0. It goes up and down forever. So what's different is it grows slowly more and more negative here. Now the most basic property for logarithms, and it's the thing that actually makes logarithms work, is you have log b of something is an answer. Well, there's an important relationship between those three items, and that is if you take the base b, raise it to the answer as an exponent, so b to the exponent of the answer, that has to equal the thing on the inside. So log 2 of 8 is 3 because 2 raised to the third power is equal to 8. Log 10 of 100 is 2 because 10 squared is 100. This basic property is the one that drives everything we will know about log functions. So let's look at the homework here. In questions 1, we have log 2 of 128 is 7. They want us to write this in exponential form. All that means is take the base, raise it to the answer, and have it equal to the item on the inside. So 2 to the 7th is 128. In question 2, we have log 1 over 100 is minus 2. So looking at this, I'm thinking, well, where is the base? They didn't write one. Well, in our textbooks and in some other textbooks, whenever you see a log with no base, it's understood that the base is 10 and you're dealing with a common log. So log with no base of 1 over 100 is really log 10. 1 over 100 equals minus 2. And so base raised to the answer must equal to the thing on the inside. In question 3, they want us to go the other way. They want us to take it in this exponent form and put it back in log form. So I need log b of something equals an answer. And what must be true is when you take the base b, raise it to the answer, it's equal to the thing on the inside. So let's see. Well, 2 is the base. Exponent is 5, so that's the exponent part. And 2 to the 5th is 32. What about e to the 0 equals 1? Alright, so log b. Well, the base is e. E raised to the 0 is 1. But if I shorten it, remember log e is really natural log, or ln. And so ln of 1 is 0. Now that happens all the time. That is another basic property of logarithms. That log any base of 1 is always 0. Because b raised to the 0 power is equal to 1. It's one of our properties of exponents. Alright, question 5. Question 5 says calculate log 9 of 81 without using a calculator. Well, how do we do that? Well, 9 raised to some power must be 81. So let's see. 9 to the 1 is 9. 9 squared is 9 times 9. So that's 81. And so the thing in the box has to be a 2. Because 9 squared is 81. In question 6, we have 2 raised to some base, some answer, must equal 1 over 64. So 2 to the something, we need to find this exponent, is 1 over 64. Well, do I know anything about 64 and powers of 2? Let's see, 2 to the 1, 2. 2 times 2 is 4. 4 times 2 is 8. Let's see, that's 3 2's. 8 times 2 is 16. That's another 2. 16 times 2 is 32. That's 5 2's so far. And 32 times 2 is 64. And so there, that is 2 to the 6th. But we need to remember a fact about exponents, and that is x to a negative exponent simply means 1 over x to that power. So 1 over 2 to the 6th can be written as 2 raised to the minus 6. And so now if we compare the two ends, 2 raised to our unknown box equal to 2 raised to the minus 6, we see that the box has to be minus 6. And so, what about question 7? Well, again, we have this log with no base, and so we know now that that's really log 10. And so we need 10 raised to some power to be 1 over this huge number. Well, let's see. 100 is 10 squared. 2 zeros has an exponent of 2. 1,000, 3 zeros is 10 cubed. So this big giant number, how many zeros are there? 3, 6, 9. So this is really 1 over 10 to the ninth. But 1 over 10 to the ninth is 10 to the minus 9. And again, reading the outside pieces, we see that the thing in the box must be minus 9. Let's see, what about ln of e to the ninth? Well, let's see. ln is a shorthand for log e, got that. And log e of e to the 9 is 9. Well, why is that true? Well, because e to the 9 is e to the 9. And so collecting together some of our basic properties so far, log b of 1 is 0. Why is that? Well, b raised to the 0 is 1. Log b of b is 1 because b to the first power is just b. And the item I just used, log b of b raised to something, I get it back. And again, that's true because b raised to that item is exactly b raised to that item. The last one here is a bit confusing looking, but is true, and I'll say more about that in section 4.4. We end this section with a practical problem. It's called the pH scale. Alright, in this last problem we are looking at something called the pH scale. And in the pH scale, we are measuring the concentration of hydrogen ions. They're little pieces of atoms that are floating around in solution. They disassociate when you put something in a liquid. So they're floating around. We're able to measure how many of these are floating around and then use our log 10 function to give us a particular number. And so this pH is minus 1 times log 10 of this particular concentration. And if we scroll down to look here, we see a pH scale. The pH scale goes from 0 up to 14. The number in the middle is 7, and that's considered neutral, and that's water. So pH of 7 is neutral, which is water. Something less than 7, such as wine or coffee or tea or lemon juice, is considered an acid or acidic. If you have a pH greater than 7, this is considered a base or basic, or you'll actually also see the word alkaline. So you have things like ammonia and bleach. So in these exercises, we're going to be rounding our answers just to one decimal place. And if you look, what they're going to give us here are two items, oven cleaner and bleach. They're giving us their hydrogen ion concentration. This is in terms of moles per liter. Those of you taking chemistry later will know what a mole actually is. It's not a little animal that lives in the ground. It's something different. And it's written in scientific notation. So 6.2 times 10 to the minus 14th and 2 times 10 to the minus 13th. Now, how do we get this notation into our calculator? We typically use a button that looks like two capital E's on it, and it turns the calculator in scientific notation mode. So let's take a look here. Let's look here at the pHs. The pH for the oven cleaner. It's minus 1 times log 10 of that concentration. Don't worry about the minus 1. The minus 1 is for a later part. So what we need is 6.2, the number, EE, to put it in the mode. We enter the exponent of 14 and then change the sign on the number. Now, if you have a graphing calculator and some Casio calculators, that's going to be reversed in that after you press EE, there's a little button that looks like a parenthesis and a minus to make the minus, and then you would enter the number. So it's going to depend a little bit on your calculator. Let me put this over here, the difference. So sometimes you might do 14 plus / minus to change the sign to give you the minus 14. And on other calculators, you might press the key that looks like parenthesis minus and then 14 to give you the minus 14. So it's just going to depend upon your calculator which one you need, and then you'll press log. Your screen should show you a negative number, so don't panic. It is minus 13.207. When you multiply it by the minus 1 in the front, that's what makes it positive. So it's typically always going to give you a negative number. So it turns into a positive one. We then round it to one decimal place. For bleach, alright, we need log 10 of 2 times 10 to the minus 13. So 2 is our number, EE to put it in scientific notation, 13 to change it to give it the exponent, plus minus to change the sign, and then log. And so we get minus 12.698. So with a negative in front makes it positive, and we round it to 12.7. Which one is more basic? Well, we have 13.2 and 12.7. So the oven cleaner is a bigger number, and so it is more basic. You might also see, as you read chemistry books or medical books or nursing books, pOH. And pOH measures the OH concentration, the hydroxyl concentration in the liquid. In a liquid that dissociates, you have two different ions floating around. pH measures the H concentration, and OH is pOH.